I don't know how many of you have actually gotten to this exercise because we didn't get any questions about it on the Discord server, so we figured we would show it here. This is based on the first tutorial that we had prepared for the topological insulator stuff, and I'm quickly going to jump into this to show you the system that we're looking at in case somebody hasn't seen it yet. This structure is basically a buckled honeycomb lattice of bismuth atoms, and this 2D structure is topologically non-trivial, and so it is a nice and easy case to demonstrate some things. And in this first exercise, you basically generate the structure and then run SIESTA, and I'm gonna go based off of this point where we already have run SIESTA to get the Hamiltonian for the structure. We're gonna use that in this second tutorial. I'm not gonna go through the whole introduction here. This basically follows a paper by Dominic Gresh and others from 2017, where they present their implementation of this method of calculating Z2 invariants using hybrid linear charge centers. Just going to briefly introduce the idea. We're looking here at 2D structures, and instead of having our wave functions as a function of two reciprocal lattice vectors kx and ky like we usually have, basically we integrate out one of these directions, in this case here the kx direction, and what we're left with is a parameter or a function that's localized in the x direction but has the parameter for the ky still in it. And in that sense, one can also then calculate the hybrid Wannier charge centers, which are like the charge centers of the Wannier functions, which are integrated above both of the, or all three of the k directions. Just here there's only one integration done. And these hybrid Wannier charge centers can be interpreted like an electronic polarization in one dimension with some external parameter ky. And then in that sense, we can interpret the Chern numbers and things like that. And yeah, and this paper then outlines, and I think this is important to read if you want to do this for yourself to really understand what's going on, how we can efficiently do this. And yeah, one important point is here, we're looking at time reversal symmetric systems. So that means all states occur with a Cramer pairs, which are related by the time reversal operator. And therefore we can exploit the symmetry where if we look at the full Briand zone in the ky direction, the two Cramer pairs are symmetric around this middle point, where if you mirror around this point, you get the other partner in the Cramer pair. So we only need to perform these calculations in the first half of this space. And then we also know what's happening in the other half. And yeah, so basically what this Z2 puck module does, and what we're going to do in a bit, is we track all these different Wannier charge centers for different states. And then we basically want to count how many times they loop around the cylinder, or how often they jump. There's one important point which makes this a little bit easier than just looking at the top and the bottom edge. That is realizing we can take any line in this first half and just count how many times the points or the Wannier charge centers cross this line. There's no reason that this boundary where we say that we basically go around once has to be at any specific line. We can choose any one. And here are some examples given. And yeah, and you can see that it doesn't matter if you take this green line or this orange line, or if you use the top boundary here, the number of intersections is always the same. And one numerically particularly stable way of doing this is to find the biggest gap between two neighboring Wannier charge centers, which is this orange line here, and follow that. it's not really important why this is the most stable one, but this makes it numerically, or makes it the easiest to calculate these numerically, because when you have many, many charge centers, it becomes easy to lose track of did they really cross this line, or did two lines just approach it and then they moved away from it again. And yeah, this this particular choice of a line to count the intersections with makes this a little bit easier numerically, and that's just why we go with it. And yeah, without dwelling more on this, I think we're just going to get started in how to do that. And yeah, like I said before, I already ran this SIESTA calculation for the first part, and you can see here all the output files of SIESTA are there. So we can just read the Hamiltonian after we load SISL, obviously. And then we define two helper functions. And if you want to do something like this for a different system, you can just use the same definition, where we're basically just defining a function where you can give a k point and then it returns the Hamiltonian in the dense format as complex numbers for the overlap and the Hamiltonian. Then there's one other ingredient that we need before we can get started, and that's the positions of all the orbitals. These are needed by the Z2PAC code. And for that, you can use a map like the one that we have indicated here in the hint to calculate these. First, we take the geometry from the Hamiltonian element that we just, from the Hamiltonian that we just read. Then we calculate the positions of all orbitals. In fractional coordinates, that's important here, that you use the fractional ones. Copy this part. And now we have the positions of the atoms basically just duplicated for each of the orbitals on the atoms. There's one more thing we have to do before we're done. Here we're dealing with a system where we have spin-orbit coupling, and that means each of the orbital blocks is blown up into a 2x2 submatrix of the Hamiltonian instead of just a single Hamiltonian element. We'll have to repeat this list twice. Position twice along the axis 0, I think. Now we still have the same list, just twice as long in each of the blocks, and we have all the positions of the orbitals correctly. That's the last thing we needed to get started. For this part, I would have to tell you to look at, where is it? Here, at the documentation of Z2PAC. We're using a Hamiltonian matrix to define our system, and then there are a couple of things we need, which is this Hamiltonian function where we just defined the shorthand function for. The basis overlap, we've also defined the shorthand for that. Then there are some other parameters here, which I'm not going to discuss right now, but we will get back to that in a minute. And then the position of the orbitals. So we have these three ingredients that are specific to the geometry and the Hamiltonian matrix now. And with that, we can create a system. There's something else that I've defined here, which is the Hermitian tolerance. The code checks whether your matrices are actually Hermitian or not. And since these are coming from the DFT calculation, and we're reading them in by with SISL again and passing them on, I found that setting the Hermitian tolerance to 10 to the -5 is reasonable. So with this, you still notice if there's something wrong in your Hamiltonian, which you might want to catch. But if you go much lower with this tolerance, then you will probably see a lot of errors because of the accuracy in the numbers not being high enough. And then here we select two bands, which are just the top two bands. And if you've done the first tutorial, you've seen that they are isolated. That's an important point here. We can calculate the Z2 invariant for every pair of bands, or for every couple of bands which are isolated from all the other ones. And the topmost two ones are separated. So we're going to start with this because it makes it much easier. We'll just have 2 Wannier charge centers. It's going to make things faster. And then at the end, we're going to add the other bands as well. If you want to really characterize the material, it's important that you calculate the Z2 invariant for all of the occupied bands, not just the topmost or something like that. So now the next point we need to define a subspace of the Brillouin zone. And that's, if we come back to this, we have to go along half of the Brillouin zone in one direction, and then we have to go along the full direction in the other Brillouin zone that is used to perform this integral here. So we have one direction in which we integrate, and then the second one along which we trace the Wannier charge centers. And to do that, we're going to define a new function of 2 parameters. The first one is always the one over which you trace the Wannier charge centers. And the second one is the one along which we integrate. We will make it easy here. We just use the Cartesian coordinates just like we've done above. We just have kx as the first component and then ky half, because we just go from the start of the Brillouin zone to the first half. These are in fractional coordinates. Yeah. And with this, we could run the calculation already. And I'm just going to do that, and then we'll revisit this part. Yeah, so what we do here is we run the calculation on a surface using the system that we just created above, the surface function that we defined. And this is just a file to save the results, so you can restart a calculation if it crashes. And then you'll see some output like this, where Z2PAC basically tells you what is happening right now. It starts by calculating the Wannier charge centers at t equals 0, then 0.1. That is the first parameter in the surface that we just defined. And yeah. So, okay. Now it has done its calculation, and we can look at the Z2 invariant that it found, and it is 1 for these 2 bands. And now let's take another look at these parameters above and what they mean. So the first step is finding the Wannier charge centers. And for that, we have to integrate along the first direction. And we've defined the surface function, but there's no number of points along which the integral has to be performed or anything like that. And how we do this is we tell Z2PAC using this iterator keyword. What this means is start by integrating using just 8 points, and then increase this number by steps of 2 until the maximum is reached here at 27, because if you don't give a maximum, it might just run infinitely. So you want to truncate this at some point. And this is also what you see here. At first, it calculates the integral using just 8 steps. Then it calculates the integral using 10 steps. And here it was done and moves on to the next point. What does it mean to be done? Basically, you compare the Wannier charge centers with this 8-point integration, then with the 10-point integration, and see if they are close enough within a certain tolerance. And that is this position tolerance. So basically, you increase the number of points in your integration until the position of the Wannier charge centers is converged. And then you move on to the next line. And then, yeah, you do the same for the next line and the next line and the next line. And then you get a picture like this one. And now there are 2 more tolerances that define whether we're done with the calculation or whether there has to be something else. One is the move tolerance, and one is the gap tolerance. The move tolerance basically means, do the Vignette centers from one of these lines onto the next one change more than the tolerance? Then we might have to add another line in between. And this becomes important, especially when you have more Vignette charge centers, because the smaller the distance here from one step to the next is, the better you can trace a given Vignette charge center without having to worry about tools having exchanged or something like that. So if this distance is small, that basically means you can uniquely trace them, and there's nothing happening there. And the other one is this gap tolerance, which is the distance between the gap and one of the charge centers in the next line. And it is important that this one is at least of a sufficient size to also basically to make sure that something is crossing along this line and not just jumping back up or something like that. But you can always plot these, and we'll do that in a minute, these Vignette charge centers and the gap, to also inspect with your eyes if it makes sense, the way they're calculated, or if there might be some ambiguity as to whether there's a jump or whether there's a Vignette charge center crossing this blue line here. Yeah. So like I said, we've provided some code to plot these, and that's more or less taken directly from the Z2PAC documentation. Here we see the two Vignette charge centers moving around, kind of making like a fish type shape, I would say. And then the trace of the gap position, which crosses one of the Vignette charge centers here, which gives us the Z2 invariant of 1, because it just crosses one time. The Z2 invariant is defined modulo 2, these numbers of crossings. So if it would jump back somewhere, or if this would go back up, then there would be a second crossing and it would be 0. Now we've done this for this first pair of bands, and there are more bands. Maybe I'll no, don't have it here. Okay. So basically, to fully characterize this this material, we would have to go back and copy this system block here. And instead of doing it just for the first, the top 2 bands, we'll do it for the first 30 bands. You can either define this as an integer, or you can pass a list of the bands. And then we basically do the same thing again. And this might take a little bit longer, because now we have all 30 bands, which means much more charge centers, and therefore much more to evaluate and diagonalize. And while this is running, I'm gonna this line of code and prepare that. Okay, I think this is close to be done. And You actually see something that I mentioned before, where it might not be clear between two steps whether this gap tolerance might not be sufficient, or this distance might not be sufficiently large. If that happens in the output, you will see something like this convergence criteria fulfilled for 9 out of 10 neighboring lines, which means that between 2 of these 10 lines, either the gap or the movement tolerance was not fulfilled, and then the code luckily automatically adds a new line in between and repeats the calculation until the convergence criteria is fulfilled between all of the neighboring lines. This is up to a certain minimum distance between the lines that can be defined, but worked here. This is something you want to watch out for at the end, whether all the checks have been passed, because that's an indication that everything went well. And then here we see, we see that the Z2 invariant is 1 indeed for the whole system. We can take a look at the charge centers again. Now we have way more here, and they move differently, but yeah, that's fine. One thing that you want to keep in mind when you do this for a bigger system is that you don't need to calculate the Wannier charge centers for all the 30 bands or thousands of bands that you might have in a system. You can partition your system, and the way you want to do that is you look at the band structure and you identify blocks of bands which are separated by some energy gap, and then you just repeatedly perform these calculations for those smaller sections of orbital of bands, and at the end you just sum up all the Z2 invariants and yeah, see if the end result is odd or even, and then you know whether the Z2 invariant is 1 or 2. The way you can do something like that is you could do something like this. You define bundles of bands, like 1, 2, 3, 4, 5, and then maybe some bands which are just always the Kramer pair, 2i and 2i plus 1, and then you run the calculation for each of the bundles, and I'll do so here because I actually see that this will not work because I haven't properly partitioned them. And this can give you a significant speed up if you want to do this for bigger systems. If you can partition it in a lot of small calculations that you can maybe even run in parallel. And, yeah. Looks good. I think. Let's see. I think this should crash because I wanted to show something. Let's wait a second. Yeah. So a crash like this one, where yeah, it says the given Wannier charge centers are not degenerate Kramer pairs at the edge of the surface. This indicates that this partitioning here of just taking the bands 10 and 11 was not correct, and they're connected to, they were not an isolated pair. So yeah, we would have to adjust that by defining how we partition the bands differently, doing 8, 9, and then maybe 10, 11, 12, and 13. This will always have to be even pairs because we have the time reversal symmetry. Like this, you can, yeah, like this, it might run. I would have to see. But basically, the important part is here, you can calculate them separately for different groups of bands, and then at the end, combine the results doing something like this, taking the sum of all the Z2 invariants that you have stored, then modulo 2, and you have the Z2 invariant for the whole system. Yeah, that's it from me, I think, for this tutorial. And if you haven't done so and are interested, you can try it yourself. For this part, I would suggest you take another look at the bands that you calculated here in the first part and plot them at the different energy scales to really detangle the bands. And if you want to do something with spin-orbit coupling for production calculations, it's important you use newer versions of SIESTA, because you'll notice that some things are not exactly, or sometimes it might look like the bands are separated when you're using this 4.15 version of SIESTA, but the Z2 invariant calculation might fail. That's because we're using an on-site approximation for the spin-orbit coupling here, which has some downsides. And what you want to do is you want to use at least SIESTA 4.2 or newer versions for this off-site spin-orbit coupling, which I think is the default from there onward and is not implemented here yet. And with that, you should be good to go. Are there any questions or anything? No questions? Let's check the chat. Okay, there's nothing there. I guess in that case, is there anything we have to announce before coming to a close?
Then I'll take over and say that this. Thank you, Niels, first.
Yeah, no problem.
So we are approaching the end of this workshop. So we would, of course, like to thank you all for participating. Without you, this wouldn't have happened, of course. We hope you have found it interesting and it has intrigued you to do some more stuff and perhaps contribute to the packages if something is needed. All contributions either to CISL, Hubbard, Elastica are always welcome. So don't hold back. Let me see if there's anything else. Of course, we would like also to thank the funding agencies, CCAM, the IPC, MAX, in particular. We would also like to thank all the tutors who have helped out with answering questions to you all. So that's Gaetano, Sophia, Nils, Jonas, Paul, and Arne, Alexander. They have all been a great help, and we hope you have also learned a lot from these excellent tutors in this workshop. Some specific people at the CCAM side have helped at the IPC, Camila Alonso and Jose Caballero. I hope I'm pronouncing that correctly. There has been much of discussions, especially related to this COVID-19 situation and the transfer of the workshop to an online situation. In particular, the format this year, it has proven quite difficult, but I think we managed to do something that is reasonable for everybody. It's not easy to do this for a large amount of groups, but perhaps if you fill the survey, this would greatly help us for future workshops. And in general, if you feel that this is a good format for doing stuff or for having workshops online, we might do it more frequently. All the material will be made available at the specified links. We've shared them a couple of times through the workshop, so you can already now access all the slides on the GitHub page. There's also a link to the YouTube channel. The YouTube videos of the lectures will be uploaded as soon as possible. The final tutorials, based on their comments, all the final tutorials will just undergo a scrutiny and some bug fixes, spelling mistakes, etc. So in a week or so, hopefully everything should be available online. Let me see. I think that's it. Please do keep in touch. Please engage in the Discord community, this Discord site that you've been contacting us through. That is meant for a continuous discussion where everybody can join, everybody can answer, everybody can. So it would be really great if the community can help each other out. And this is sort of an informal way of contacting each other. So please do share your scripts, your codes, your ideas, share them there, discuss them, and perhaps perhaps everybody can learn something from everybody here. Is there anything else?
Well, thanks to you, Nick, for coordinating everything so well. And thanks to everybody for a nice time here in a virtual setting.
Yeah, and of course, thanks to all the poster presentations on Wednesday that I probably forgot that. So thanks to everybody and enjoy. Bye-bye.
Bye-bye. Bye-bye.
Bye.
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 Bye.